Hello, let's do a quick guide of the equation booklet that will be in the exam with you. The equation booklet contains a lot of useful information. So I'll be going through it, highlighting any laws using red pen, any definitions using green pen, any origins where needed, where the equations come from, literacy in pencil. I'll be highlighting energy using a pink highlighter. I'll be highlighting forces using a green highlighter, and some accelerations using a yellow highlighter. The next section we have is the electric field section. In it we have a couple of forces that could be joined onto any other force, and we have an energy down the bottom that could be joined onto any other energy on there. We start the show with a definition, the definition of electric field strength, and this is the equation that would define that. We would say it in response to a literacy question as the force experienced per unit charge. The next equation is Coulomb's law. I'd like to think that everybody's well practiced at saying this one. It's identical to Newton's law of gravitation. The force between two charges is directly proportional to the product of those charges and inversely proportional to the square of the distance between them. So looking at the equation, you ignore the constants down the bottom. The force between two charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. Next we have an equation. It's not really a definition now. This definition is at the top here. This is an equation for electric field strength again. This is electric field strength around a point charge. The one below is electric field strength again, only this time it's for parallel plates, between parallel plates. Next one, this V is a definition. This is electric potential, and this is not one where you would say what you see with regards to the equation. This one you'd have to say the definition of electric potential is the work done to move very specifically, a +1 Coulomb charge from infinity, where the potential is 0, to a point in an electric field. The next equation down is also a definition. It's the definition for electric potential energy. And to put that into words, I'm literally going to copy what I've written above, only change the charge bit. So instead of it being a +1 Coulomb charge, it's going to be anything. So electric potential energy is the work done to move a charge, so it could be anything, a charge, from infinity to a point in an electric field. You should make a comparison between electric potential, the definition in the equation, to gravitational potential, the definition in the equation, and you should make a comparison electric potential energy, the definition in the equation, to gravitational potential energy, the definition and the equation. What we need to do now is highlight this one in the middle, the electric field strength between parallel plates. That electric field strength would be uniform, a constant value. I'm just going to put electric potential divided by, this is a distance. That distance could be a radial distance, and that means that I can link, by putting this V in there, I can turn electric potential by dividing it by another radial distance. I'll end up, instead of just R at the bottom, I'll end up with R squared. This is where electric field strength equation comes from. So these two equations, this one here and this one here, are linked by this equation just expressing the distance as a radial distance instead. But I'll keep going because we can also say that electric field strength is, going back to the top here, force per unit charge, and we can take this V over D equals F over Q and get an expression for the force experienced by a charged particle moving between two plates that have a potential difference V across them, separated by a distance D. And then using Newton's second law, we can divide everything here by mass, and a force divided by a mass would be an acceleration, and we can work out what the acceleration experienced by that charge would be. The value of its charge, the potential difference across the plates, the distance between the plates, and the mass of the charged object. And quite commonly that would be used in some sort of SUVAT equation some sort of SUVAT question, where this would be how you would calculate the acceleration. S would probably be, it depends on the question, could be the distance between the plates and you, so on and so forth. The other parts that we need to highlight in this section are how some of these equations link together. So down here I've got energy, and above it I have potential difference, a voltage effectively, an electric potential. And the definition of the volt is the amount of energy carried per unit charge. V equals E over Q. So if I were to take my expression for energy and put it into that equation, I would have to take this expression, divide it by Q. One of the Q's would disappear, and I would be left with this equation. The other thing that's used to link some of these equations together over here, I'll just write work done equals a force times a distance, but let's make that a force times lowercase r, or radial distance, and then I can take my force, Coulomb's law force, the force between two charges, pop it in there, times it by lowercase r. That means I'll lose the r squared will just become r, and then that represents where my electric potential energy equation comes from. So the difference between these two equations, this one here and this one here, is that the one at the top for force has got r squared, and the one at the bottom doesn't have r squared, and the reason for that is because of this equation over here. It's quite common for Coulomb's law, which we've got here, to be linked to, sometimes I've seen this a couple of times, the Coulomb's law can be linked to circular motion, so F equals mv squared over r, quite a common thing there. And the last thing I'd like to add is the linking together of Coulomb's law and the electric field strength of a point charge. Linking together these two equations, this is quite messy, but if I was to, I can link these two together using the definition for electric field strength, and I would literally get this force, put it into that equation as the force there, which means I've got to divide it all by Q to get an electric field strength. So all of this divided by Q would remove one of the Q's at the top, which is the equation we have down at the bottom. So that is where that comes from. So I'm going to jump over that line, and we're back in there. All right, really messy, but if you know how it's all linked together, it really does help in the exam, really does.